Welcome back. Today we're starting a new section in our statistics module, parameter estimation and fitting distributions. This is a really central idea in data analysis and statistics, and is especially relevant today because it's the basis of much of modern machine learning. So the idea here is we're going to collect data from a system, and we are going to try to find the best fit distribution, probability distribution that describes that data. And we might do this, for example, by taking a known distribution like Poisson or exponential or normal and finding the parameters of that distribution that best fit our data. Okay, so today this is the overview. We're going to have a bunch of lectures on this topic. I'm going to tell you kind of the classic way of doing this using probability models, the modern way of doing this in machine learning, and we'll have a code example that I think is pretty useful that we'll use throughout this lecture series. Okay, so let's get started. So the classic approach, I'll just write it here, kind of the classic approach, is you start with a model of what you think your data is probably described by. Kind of you use first principles arguments and probability to build a model of your system. So essentially we collect data. So we collect data and we use probability arguments and use kind of probability arguments to guess or to posit a best model that we're going to fit, to essentially posit a distribution. Okay. Now, for example, let's say we know that radioactive decay, we think that this is governed by a Poisson process. So in fact, I'm actually going to write this down as the primary example we're going to look at. So the example here, and I'm going to have a code in a minute, is radioactive decay. Radioactive decay, where we will actually have data. This is from a 1966 paper of Americium, I believe, Americium decay, and we will have like data for how many atoms are, decay in a certain interval of time, and we're going to posit that this is a Poisson random variable, kind of how many atoms decay in a certain fixed interval of time with some lambda. And so the idea here is we have a kind of physical or probabilistic argument that our data should be Poisson, and there is an unknown parameter that we are going to fit using observed data. So that's what we mean by parameter estimation. We're going to estimate this parameter from data, and we're going to fit the distribution that best fits that data. This is the classical approach, and it's still super useful today. If you think you have data that's described by Poisson or exponential or Gaussian or gamma, any of these named distributions, that gives you a very few parameters you have to estimate to fit that distribution. It's really kind of easy, straightforward approach to do that. We're going to talk a lot about this, even though what we ultimately want to do is fit distributions where we don't know, the distribution in machine learning. So let's write that down. Kind of the modern thing we would do, and by modern, of course, I mean machine learning, ML. The modern approach is essentially we collect data and it probably doesn't fit a nice named distribution. So we collect data, same as before. We collect data. We always collect data, because this is statistics, this is kind of data analysis. We collect data, and it does not fit a nice named distribution. So lots of examples of this. If you think about image classification or natural language processing, lots of examples in machine learning. The data, there is some underlying kind of joint probability density of the data, but it doesn't fit, Poisson, normal, exponential, things like that. So some examples are things like, natural images, material properties. There probably are PDFs that describe these data, but they're probably not named distributions that we have learned, out of our textbook. Turbulence is another good example. We know that there is a probability distribution for turbulence. You can kind of measure and plot it, but it's hard to write down a named distribution for, the distribution of velocities in turbulence, natural language processing, and so on and so forth. Many, many, many examples in this kind of second paradigm where our data does have some underlying distribution, but it's not like a nice textbook distribution. And in all of these cases, maybe I'll switch to yellow, in all of these cases, typically in the machine learning applications, your data, your kind of probability density function that you're trying to estimate, this f of x, it's going to be high dimensional. So for images, usually you're dealing with megapixel or higher images. So that's like a million dimensional vector representation of that data. So it's high dimensional. There's usually some messy joint probability between all of the pixels or all of the velocities or all of the different materials properties. So kind of joint PDFs. Pretty complicated joint PDFs. And sometimes if I think about these PDFs and kind of where the data lives in a fractal subspace or manifold of this high dimensional measurement space. So I'm going to put down some words like fractal, kind of nonlinear, and so on and so forth. These are complicated. There's not going to be a nice distribution to describe these, but we can still collect data and fit some distribution. Here, we're going to fit the distribution, the parameters of a known distribution. Down here, we might model the distribution as a neural network. And in that case, the parameters are the weights of the neural network, or whatever other machine learning architecture you're using. There will be some free weights that you optimize to best fit that data. That's also a parameter estimation and distribution fitting problem. Classic and modern. Okay, good. So these are some of the things we're going to talk about. I want to show you a code example that I think is really useful to get you thinking about what we are going to be doing. Then I'm going to write down the mathematical formulation of this problem, and then that'll be the end of this lecture, and there will be a lot of deep dives into these specific topics. Okay, so let's do this code example. And I got this code example from the textbook by Rice, which I think is a really good textbook. A lot of what I'm doing is kind of, at least roughly follow some of the material in Rice. And so this is an example from Rice that was pulled from a 1966 paper where the radioactive decay of a radioactive element is being, it's Americium 241, that's the radioactive element. Its decay is being measured and trying to fit a Poisson distribution to that measured data, because we think that radioactive decay is a Poisson process. Okay, so I'm going to tell you very briefly what the data is. We're going to plot a histogram. We're going to quickly, using quick and dirty techniques, fit a Poisson distribution and show that it's not a terrible idea. And in following lectures, we're going to justify our choices, analyze the error, do all kinds of proper statistics. Here I'm just getting kind of showing you a teaser of what we're going to see next. So the data is actually super cool. In this experiment, they collected about 10,000 Geiger clicks, which means the Geiger counter is counting the every time an alpha particle is emitted from this Americium 241, this counter clicks. And there are over 10,000 clicks, and they measured the exact time between all of these clicks. So they measured the time between about 10,220 alpha particle decays, emissions. And we know that the time between emissions is an exponential process, and the number of clicks, the number of emissions in a fixed interval should be a Poisson process. So what they did was they binned this data into 10-second intervals. So the number of alpha particle emissions in each of those 10-second intervals should follow a Poisson process. And then what they did, all of those 10-second intervals, they counted how many alpha particles were emitted in that 10-second interval, and in the next 10-second, and the next, and the next, and the next, and the next. And so the data here in this line, observed counts, what this does is it says, okay, the first bin, maybe I'll plot the data and we'll actually talk about it this way. It's a little easier. So the first bin of data, the 0 bin, that is how many times in a 10-second interval no alpha particles were measured. And the second bin, this x-axis equals 1 here, that is the number of times in a 10-second interval exactly 1 alpha particle was measured. The next bin is how many times in a 10-second interval 2 alpha particles were measured, and so on and so forth. And you can see up here, like in bin 5, that says that there were about 110 intervals where 5 alpha particles were measured. And so that's what this vector of data is here. This is the raw data from this 1966 paper, and here we're plotting the data as kind of a histogram or a distribution, okay? And if you look at it, it looks like it could be a Poisson, maybe it could be normal. It's a little hard to tell. We know that Poisson starts to approach normal for large n, but anyway, this is what the raw data looks like. And we're kind of trying to find the best Poisson distribution that best fits this data, okay? So that's a very reasonable thing to do. What is the lambda based on this data that best fits that data? So the simplest thing to do, we know that lambda is the kind of expectation value of x. It's the expected value of x, the average, the expected average of x. And so over your sample data, over all of this data, we could calculate the sample mean and use that as a best guess for lambda. Let's call that, in fact, we're going to call that lambda hat equals the sample mean x bar. That's a pretty good guess for the parameter of this Poisson distribution. And again, I'm going super quick and dirty here, just the basic idea. We're going to justify this choice later. But here what we're going to do is actually calculate the sample mean, okay, based on the data. And then we're going to fit a Poisson distribution using that lambda value, that sample mean. And then we're going to plot that fit with the actual data. So let's do that now. And now you can see the data and the best fit Poisson distribution. So the best fit Poisson distribution is in cyan. It does a really, really good job of capturing this data. It's actually super, super accurate, okay? So this at least gives us a rough idea that we can take ideas that we learned in probability theory, like, how the parameter lambda relates to the expectation value or the average value expected for x, and we can use that to get a best fit of this parameter based on our observed data, okay? And this actually does turn out to be a really good estimate for this lambda parameter. We'll derive that later, but this just shows that it's reasonable to do that. Okay, there's other questions we might ask. Okay, so that's it for the code example. We're going to come back to this example over and over and over again. We're going to do fitting and hypothesis testing on that example. So we're gonna see more of that later. Other questions we might ask. The first question was, what's the best fit parameter that best fits this data? Another question would be, is Poisson even reasonable? Is Poisson a good fit? And so we can actually do a hypothesis test. We can write down a hypothesis that the distribution is Poisson with this lambda or is not Poisson with this lambda. And we can do hypothesis testing and actually get confidence intervals and rejection regions and all of that as well. So there's more other questions we might ask. What is the error in my estimate? What is the error in estimate? Lambda hat. How large of a sample do I need to make that error smaller? Is there a bias? All of the things we asked in the survey sampling and sample statistics we can ask here too. So we can do hypothesis testing, we can build models for the error in these estimates, and we can find best parameter values. Good. And in either case, either for classical parameter estimation and data fitting or modern machine learning distribution fitting. In either case, there is a mathematical way of writing this problem down that we're going to find very useful. And all of the examples of methods to answer these questions are going to be based on this mathematical formulation I'm going to tell you right now. Okay? So in either case, so yeah, let's just write this down. In either case, kind of the classical or the machine learning case, in either case, we parameterize some distribution. We parameterize some distribution. Now, that distribution might be a known distribution like Poisson, or it might be an unknown distribution like a neural net. The weights of a neural net might be the parameterization of our distribution. So we're going to say that we have this f of x given theta. So x is our variables, kind of the data variables, and theta are our parameters, okay? And this is our kind of variables, our random variables. And this f of x given theta is literally the probability that our random variable equals this value x given the parameters theta. So for example, in this Poisson example, you could literally take the Poisson PDF as a function of lambda, and that would be this function x with, with respect given theta. So parameters. So for Poisson, theta is our lambda value. For a normal distribution, theta would equal a vector of mu and, let's say, variance. Okay, so whatever your distribution is, you can parameterize it. We're just going to call those parameters theta, and we're trying to find the theta that best fit our observed measurement data. And in a neural network, in the machine learning version, theta are the weights of your neural network, or the weights of your machine learning model that you're trying to tune or fit or optimize to best fit the data, the observed data. Okay, pretty easy. So the mathematical statement then is that we are trying to find theta. We want to parameterize some distribution and find theta to maximize this probability, to maximize the probability. And in some sense, to be most consistent with the observed data, okay? So if we literally find theta that maximizes this probability of x, of our data equaling x, given those parameters, that would be a maximum likelihood estimate. So this is the method of maximum likelihood estimation. This is a very common, you'll hear this all the time, MLEs, maximum likelihood estimates. This is a super, super, super popular way of finding a best parameter for a probability distribution based on data, okay? So it's really intuitively simple. There's some PDF, maybe I'll even just draw a little picture here. So I could have some PDF, and let's say it's, a Poisson distribution. So I have whatever the PDF of my Poisson distribution is, and I can vary that parameter lambda. So there's a whole family of distributions varying this theta or this lambda parameter, and I can vary all of those, this lambda to get this whole family of Poisson distributions. And I have some data, I have some actual measurement data, and maybe my data, looks essentially like this. So what I'm essentially trying to do in your cartoon in your head, what we're trying to do is we're trying to find the lambda that makes the distribution f of x given lambda best match the observed data. There is a lambda that will be most closely matched to that data, and that's what the maximum likelihood estimator does, is it finds that best fit parameter theta. In the case of Poisson, our parameter is theta equals lambda. Okay, so here theta just is a generic parameter variable, and then in specific distributions we'll use specific variables like lambda or mu or sigma squared. Good, so that's the idea. We're trying to find theta that maximizes the probability of our data fitting that distribution. That's how we say this mathematically. And this should seem very, very closely related to Bayesian optimization, to Bayesian statistics, because it is. So there's this kind of dual problem. We know the probability density, at least in the classic case, we have f of x given theta, and we're trying to find theta. But what we actually want, we want the probability of theta given x. This is like the Bayesian inverse. This is literally the Bayesian inverse. The Bayesian or statistical Bayesian inverse. If we knew the probability of a parameter given the data, we could just plug in the data and read off that parameter. Like that would give us the maximum, likelihood estimate parameter. But oftentimes we just have this kind of forward model, and we have to write it down as an optimization problem to find the best theta. I'll show you how to do this all in the next few lectures. We'll derive the MLE formulation. We'll do it on normal and Poisson. We'll talk about the connection to Bayes and how to incorporate priors into maximum likelihood estimation. This is all coming up. There is kind of an alternative perspective that's also pretty useful. So maybe I'll just write down, this is a big one. Maximum likelihood estimators is a big thing we're going to talk about. Another big thing we're going to talk about, another way of estimating these parameters given this distribution is called the method of moments. So in the method of moments, what we're going to do is we could express theta in terms of moments of my probability distribution, of moments like mu k, the mean, the variance, and the higher moments. Let's say mu1 equals the expected value of x, mu2 equals the expected value of x squared, and so on and so forth. We could write our parameters in terms of these moments. For example, we know that lambda is equal to the first moment, and we know in the normal distribution mu is equal to the first moment, and sigma squared is related to the first two moments. So we can write down these thetas in terms of these parameters, and then we essentially use data. We use our random variable data, xi, our actual sample data, to estimate these mu's. Let's call them mu hats, and therefore we can estimate our parameters. We'll call it theta hat. This is a really, really popular, easy method when you know your distribution. When you can write down these parameters in terms of the moments of your PDF, then you can then estimate those moments with data and then get an estimate of your parameters from that estimated. That's what we did in this Poisson example. We know that lambda is related to the expectation the first moment of x. So we computed the sample mean, which is the data approximation to the first moment of x, and we plugged that in to get lambda hat. We just did the method of moments in our code example. So actually, I'll probably show you this one first because it's easier to explain. So this will be the first one, and this will be the second thing I show you. And then a couple of other things that are important. Distribution fitting is very closely related to hypothesis testing. This question here, is a Poisson even a good fit? I can find the best lambda that fits my data, but what if my data isn't Poisson? I can find a lambda, but it's still not a good fit. Is my distribution a good fit? This is related to hypothesis testing. So we will do some examples of hypothesis testing in this parameter fitting and distribution fitting. Do the distributions match? We'll use something called the chi-squared test. We'll talk about the KL divergence, and so on and so forth. There's a bunch of different methods to test if a distribution is actually matching your data. Okay, so this is all coming up soon. Big picture is that we have data and we want to find the best kind of probabilistic distribution that fits that data. This is a statistics problem because this is based on actual data X, these kind of random measurements of my system. And we are going to do the method of moments, maximum likelihood estimation. We're going to talk about the Bayesian connection and hypothesis testing. And a lot of it we're going to do on this radioactive decay example that I showed you a minute ago. That's all coming up. This is one of my favorite sections. Super interesting stuff. Stay tuned for more. Thank you.